In electrophilic aromatic substitution, the existing substituent on a benzene ring dictates where the next group will land. Today, we explore why certain groups, known as electron-withdrawing groups, specifically direct incoming electrophiles to the meta position. Groups like nitro, cyano, or carbonyls are strongly electronegative. They pull electron density out of the aromatic ring through both inductive effects and resonance, making the entire ring less nucleophilic and overall less reactive than benzene itself. Because these groups remove electron density, the ring becomes deactivated. This means the reaction requires more energy to proceed. However, the reaction still occurs, and it chooses the path of least resistance among the available positions. When an electron-withdrawing group is present, the meta position becomes the preferred site for substitution. To understand why, we must look at the stability of the intermediate carbocation formed during the reaction mechanism. The reaction proceeds through a sigma complex where the aromaticity is temporarily lost. The stability of this intermediate determines the speed of the reaction at each specific position, ortho, meta, or para. If the electrophile attacks the ortho position, one resonance structure places the positive charge directly on the carbon attached to the electron-withdrawing group. This creates a powerful electrostatic repulsion between two positive centers, making this path very unfavorable. A similar problem occurs with para attack. One of the resonance contributors places the positive charge immediately next to the electron-withdrawing group. This destabilizes the entire intermediate, significantly raising the activation energy for the para pathway. In meta attack, the positive charge is distributed among the other carbons but never lands on the carbon directly attached to the withdrawing group. While the ring is still deactivated, this path avoids the most unstable resonance structures. By comparing these intermediates, we see that the meta attack is not activated in the traditional sense, it is simply less deactivated than the ortho and para positions. It is the most stable of the available high-energy intermediates. Let's look at a real-world example. When we nitrate nitrobenzene, we get nearly 93% meta product. The harsh conditions required, concentrated acid and high heat, reflect the deactivated nature of the starting material. Some reactions, like Friedel-Crafts alkylation, fail entirely on deactivated rings. The electron-withdrawing group makes the ring so electron-poor that it cannot react with the relatively weak electrophiles used in these processes. Consider benzaldehyde. The carbonyl group is electron-withdrawing. During bromination, the bromine atom will be directed to the meta position because that transition state avoids placing a positive charge next to the partial positive carbon of the carbonyl. Visualizing the electron density map, we see the ring is overall electron deficient. However, the metacarbons retain slightly more density than the ortho and para carbons, making them the most attractive targets for an electrophile. To summarize, electron-withdrawing groups deactivate the ring. They direct meta because the meta-intermediate avoids the extremely unstable resonance structure where the positive charge is adjacent to the withdrawing group. Remember these 3 points: EWGs slow down the reaction, they create unfavorable charges at ortho and para positions, and the meta position becomes the default major product by process of elimination. Let's test your knowledge. Which of these is a meta-director? Methyl and hydroxyl groups are electron-donating. The cyano group, or CN, is electron-withdrawing and thus directs the incoming group to the meta position. Understanding these electronic effects allows us to predict the products of complex organic syntheses. By analyzing resonance and inductive forces, we can master the behavior of aromatic systems. Generated by Vision Solve AI.